Okay, so the plan for the next 4 days, well, today and the next 3 days is today we finish, hopefully, one-dimensional momentum. Tomorrow we finish what? Two-dimensional. Are we going to do 3D? No. Could it be done? Absolutely. If there is something in 1D, there is something in 2D and 3D. Most likely, even in university, they barely even touch up on 3D momentum, but it still could be doable, especially after you take the very last section of MCV for you. How many people are doing vectors now? Yes. So technically, it could be done, but we're only gonna keep it to 1D and 2D. And Thursday and Friday will be just university problems on this stuff, and that will be the end of the unit. Okay. All right. So momentum is a physical quantity that is actually very simple to define, but is so central to all of physics and nature. It is defined just to be mass times velocity. Mass times velocity. What can you tell since there's velocity in it? Momentum has to be a what? A vector, exactly. Whenever you combine a scalar, which is mass, and a vector, which is velocity, vector always wins. Vector nature of any addition, or sorry, of any multiplication or division always wins. Okay? So Newton actually called it the quantity of motion. The quantity of motion. But the official name would be just momentum. Okay? So it's mass times velocity. Okay. So that's the basic concept of it. So now we go back to vectors. That's the thing. All of energy was what? All of energy was scalars. Now we go back to vectors. Okay. So the physical symbol for momentum is, oh, I don't care, open any physics textbook in any grade or any university year, it's always going to be lower case p. Lower case p. With a what? With a vector sign on top of it, or an arrow on top of it, because it is a vector. It must have a direction. Well, now you know. It must have a direction, but we have our ways of what? Of still treating every vector as a what? As a scalar, either positively or negatively, just like we did with kinematics, just like we did with forces, and so on. Okay? All right. So this would be the equation for it. Oops, my bad. So momentum is always defined to be mass times velocity. Remember, this m cannot have an arrow on top of it because it's never a vector. Mass is always just a scalar indicating how heavy any object is. So P is equal to m times v. This very simple equation is actually the building block of pretty much most of physics. Doesn't matter if it's quantum or classical, most of physics actually is based on that, and you will see how. Obviously, we'll do it only in the realm or in the mindset of classical physics only. By classical physics, I mean particles that are not very small and also not very fast. If it's very small, it's quantum. If it's very fast, it's relativity and speed of light. These two things we don't touch until the very end of the course, maybe for a couple of days stops. Okay? All right. Here's the thing about momentum. It doesn't actually have a famous person's name as its unit. Like what? What has a person famous names as a unit? Newton for forces, Hertz for frequency. What is it for work and energy? Joules, exactly. Yep. Momentum actually doesn't have it. Momentum doesn't have it. Momentum unit is legit just the what? Just the multiplication of the unit for mass, which is just kilograms, and the unit for speed or velocity, I guess, which would be the same, which would be meters per second. So there are two ways to always what express it, either with the slash or one of those two. I've seen some books sometimes, do this, or I'm going to use this most of the time. However, here's the good news, everyone. You will almost never see me use this unit for momentum. Actually, you'll almost never see me what? Use any unit for momentum. Not because it doesn't have a unit or because the unit is not important. Units are always important, but because of one very important thing about momentum. Momentum is always conserved. So because it's always conserved, what does that mean? Initial momentum is always going to be equal to what? Final momentum. So we'll always going to skip what? We're always going to skip the the unit as long as everything is standardized. Now you might ask, hold on a second. Well, we still did conservation of what before? For almost all of last week, we did conservation of what? Energy. Yet we still called it what? We still called it. We still kept joules after every single quantity. For some reason, whenever you do, I've never seen anyone bother with what? with the units for momentum after. As long as you standardize everything to what? Kilograms, meters, and seconds, you're fine. That's it. We just got to worry about the numbers. As long as every unit is standardized. That's all. Okay? Which makes things easier, I guess. All right. So this is already filled in for you. The only physical quantity in this universe that is always conserved is momentum. Now I know, I told you already that the other conserved unit is also quantity is always what as well. What's also conserved? No, not mechanical. Total energy. Mechanical only if you have what the two players, right? If you have more than two players, like if you add thermal and elastic and all of that stuff, you have got to call it what? Just total. Mechanical is only if you have the K and the G. Here's the thing though. If you don't have a sealed closed system, could energy still be lost? Yes. Here's the thing about momentum. Momentum could never be lost whether the system is what? Sealed or not sealed. See, the problem with conserving energy is that you really have to worry about every single player and every single aspect of the system. Momentum circumvents that problem and it's always conserved. Yes. You had a Yes, exactly. Yes. Okay? In other words, when some event happens, a reaction, be it a physical or a chemical reaction, a collision, we're going to do a lot of these, an explosion, we're going to do a few of these as well. A transformation of any kind, anything could be lost or gained, including mass could be gained or lost, energy could be gained or lost, temperature could be gained or lost, heat could be gained or lost. Well, heat is another form of what? Of energy, basically, thermal energy. Except for what? Except for what? Momentum. Momentum of a system right before the event and right after the event is always 100% conserved. How important? How important is this idea? Even when they collide particles at CERN, like protons and neutrons and all that kind of stuff, the first step in any problem is to analyze momentum and require it to be what? To be conserved. To be conserved. Once you say it to be conserved, all the physics will follow suit. And to this day, it has not been violated once. Well, it was violated, they would actually be discovering that a lot of old physics and new physics is wrong. Well, so far, no one has discovered that. Okay? So remember, momentum is always the first step in almost any physics problem. Not for you, but in general for advanced and engineering physics. Okay? All right. So, what is the statement for conservation of momentum? What is the statement for conservation of momentum? Similar to the what? Similar to conservation of energy. There you go. Go ahead. I think it's actually written for you. It is fully. Yes, it is. The sum or total of all the momentums. By the way, momentums is the wrong way to pluralize momentum. Does anyone know how any word that ends in um is pluralized? Like, when you have more than one? Yeah? Well, actually, that's if it ends in us, like syllabus or fungus. Fungus, fungi, right? Momentum, or curriculum, you make it an A. Momenta, curricula, and so on. But you know what? Let's just go with momentums for today. So the sum of all the momentums of all the system before the event is exactly equal to the sum or total of all the momentums of a system after the event. So how would we actually write that in a mathematical notation? There we go. Go ahead. So sum of incoming momentum vectors must equal sum of outgoing momentum vectors. By the way, that's your first box. That is your first box. So if you want to say that in what? In a mathematical way, you say momentum total before collision. By the way, I know that it's not only a collision. It could be a collision. It could be an explosion. It could be a transformation. It could be a reaction. It could be absolutely anything. We're going to deal so many times with collisions. I guess that's why I say collision. Even I've noticed a lot of textbooks as well use the word collision as an umbrella term for pretty much any event that happens. Okay? So P total before collision must equal the P total after collision. Which means what? If you have a bunch of objects about to hit each other, you take the momentum of object one initially before it touches like the collision point, plus the momentum of object 2 initially, plus, 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 and you make that equal to the momentum of each object added up after the collision. Remember, this is theory so far, so it doesn't make much sense. We're going to do examples right now after this slide. Just 1 second. Let me. Yep. By the way, I posted all the videos for last week, so everything should be up on the YouTube. Yes. Of yes. How? Yeah, you're absolutely right. How is it conserved? Momentum actually. Okay. Give me something else that also relies on the velocity of an object that we took last week. Hmm. What other equation has speed in it that we did a lot last week? EK. It's because of that. Basically, the transfer of energy in between the particles of the system is what makes what momentum and both energy conserved. Momentum actually is another manifestation of energy. Think about it. Can you? Okay, question, everyone. If a speed has zero speed, if an object has zero speed, what's the momentum? Zero, because mass times v. So both momentum and energy depend on what? An object that has to be in what? In motion. There you go. So basically, because of the slowing down, means what? Energy is going just to what? Another part of the system. That's why momentum is always conserved. Velocity is not, but the effective velocity is what makes both momentum and energy conserved. You'll see it when we do examples, okay? Okay, so let's actually now what? Do the second handout, okay? The one with the car in front, like the first example. Okay, so let's take, remove, end this show. Okay. All right. 1D momentum. There we go. Okay. This might look slightly different. I changed your slides, but not the old slides for the teacher from last year. But it will have this exact same content. Okay. Okay, everyone, just pencils down. Let's just read a problem. By the way, almost every 1D problem for a collision is going to somehow read like this. So a 1,350 kilogram car traveling, which means it's already in what? In motion. Perfect. At 72 kilometers per hour, in which direction? South. Okay, so we know the mass and the velocity of this car. Awesome. Collides, which means comes into contact with another car, and they're telling you it's already what? They're telling you it's what kind of a motion? Slow moving. Okay, fine. Whatever that means. Of mass 1650, also initially traveling which way? South. Does that happen? Yeah, all the time. That's how you what? That's how you rear end someone, right? You're speeding, sorry, you're going, and you couldn't what slow down in time. They already what started moving, you know, after the light turns green, but you actually what rear end them from what? From the back. Okay. After the collision, by the way, after the collision means immediately after the collision. Immediately after the collision. How immediately is immediately? I don't know. A nanosecond, a femtosecond, whatever. Immediately after touching, the velocity of the two cars together is how much? How much? So that means what? The car from at the back went from what speed? 72 to what? To 24. Does that make sense? Newton's third law. Every action has a what? Has a action. The car at the back hit the other car in front, which means what? It affected with which force? Backward or forward? Forward, which means it was itself affected with what? Backward force. Could you ever hit a car and speed up? No. You must what? Slow down. The other car is gonna what? Speed up. Exactly. Energy transfer. Yes. Sorry, say again. 72. And by the way, we don't know how fast the other car was moving, but they're saying it was. Okay. In the same direction. That's what the question is claiming. No, no, no. We just know that when they collided, immediately after the collision, one of them slowed down and one of them what? Sped up. The one that slowed down went from 72 to 24. The other one, we don't know what the initial speed was pre-collision, but we know immediately after the collision, it went to what speed? 24 kilometers per hour. Is that making sense? That's it. The question is simple. How fast was the front car moving right before the collision? Okay. Is this a collision? Yes, it is. We're going to apply what? Conservation of what? Conservation of momentum. All right. So let's see. Okay, everyone. Which car is this one, front or back? This one's the back. Okay. What's the mass of this car? Come on. Now we're going to put some numbers on this. So the mass of this car is, oh, sorry. First of all, the speed. 72 kilometers per hour. How do you think I got the 20? What's the magic number for conversion between kilometers per hour and meters per second? 3.6. So if you divide 72 by 3.6, you perfectly get 20. Perfectly get 20 meters per second. Okay. And the mass is, I believe I have them. Okay. Now, do we know the speed of this one? Come on. No, no. We don't. But apparently, they said it's moving which way? South. So I guess we are designating this direction to be what? This direction to be south. So this one is moving south. Do I know the speed though? So I need to what? I need to call it a variable. What could you call this as a variable? V of which car? 1 or 2? 2. Final or initial? So this would be the speed of the second car before the collision or in the initial stage. However, because we already know all the other speeds, you can just call it V2. You can just call it V2. Although you are more than welcome to call it V2I if you are very adamant about calling everything either initial or final. Okay. Which direction are we going to designate to be positive? That way or that way? Yeah, the motion, the existent direction. So go ahead. Yep, come on. By the way, every 1D problem should always be treated like this. Go ahead. What does P car 1 mean? P, what does it mean? Momentum. So this is the momentum of car 1. By the way, are we doing the final or in the initial stage so far? Only the initial stage so far. All right. 1350. Why do you think I have a plus here? I mean, I don't have to, but why do you think I put it up here in the notes? Because it's mass times what? What's the definition of momentum officially? Mass times what? Speed or velocity? Velocity. Velocity is a vector. Vectors could either be positive or, because they could either be forward or backward. So I'm just emphasizing that the momentum of this car is pointing which way? It's pointing which way? The south, which is designated to be the what? The south. Sorry, the positive. Okay. Do I know the momentum of the black car? Do at least I know a part of the momentum? Yeah. Which part? The speed or the mass part? The mass part. Okay. Go ahead. What do I do? Yes, Nora. No, no. Okay, everyone. We are gonna just put that up under each instant, and then all the analysis will be done here. So everyone, we are not gonna do more than this under each part of the picture. So don't worry, you're not gonna have to write too much in the space between the two pictures. Technically, what should I do with these two? Technically, what should I do with these two? Is the momentum conserved individually or in total? Exactly. Okay. Again, we're not going to add yet. We're going to save that to the what? To the other slide. After, what did the cars do? They were in what? They were in contact for a very brief time. It's because they collided. Okay. Technically now, are they two separate or one individual mass? One individual mass, okay, as far as we're concerned, because they are both moving exactly at the same speed now. Okay, so this is after. Now, what's the speed here? Right after the collision. 24 kilometers per hour needs to be divided by what? 3.6. If you divide 24 by 3.6, you get an infinite number of sixes. Yep, exactly. So 6.67 meters per second. Okay. By the way, everyone, technically, could you still treat them as two individual masses? Yeah, you could. I mean, you could say, okay, P of car 1 after collision is 1350 times plus 6.67 equals whatever. P of car 2 after collision is 1650 times plus 6.67, whatever. But technically, is this a common factor between the two? Yes. So that's why I am claiming I could basically assume it's one single heavy mass. The math is the same if you choose to do it the other way. I'm just trying to give you a slightly simpler way. There we go. Go ahead. That's it. That's the last thing for this diagram slide. Go ahead, come on. Okay, so I added them. Obviously, if you add 1350 by 1650, you get a very good number. Exactly 3,000. Exactly 3,000. Both of the cars together. 3,000 times 0.667. Actually, if you really multiply 3,000 by 6.67, you should get slightly more than what? Than 20,000. But I multiply by the fraction version of it. That's why you get what? 20,000. By the way, 6.67 is another way of saying what? 20 divided by 3. 20 divided by 3. Yes, that's why if you multiply 3,000 by 20 divided by 3, the 3,000 is going to divide the 3 into what? Into 1,000. 1,000 times 20 is exactly 20,000. With the you want to add a decimal here, that's fine. You want to say, you know what? We know it's going to be 20,000. It's completely up to you. Okay, can someone tell me what should I do now? What did we say about total momentum of a system? It's always what? Say it. It's always equal, or it's always what? Conserved, which means what? Technically, if I add these two, they must equal what? Those addition of those two must exactly equal that. And that's exactly what we're going to do for the next slide. Okay? All right, now let's go to the what? To the line slide. To actually write the equations. Go ahead. By the way, you don't have to write before collision. What's another word you can use before collision, after collision? Initial and final. Go ahead. But I want you to see the word total. I always want to see the word total because I always want to see the T in ET with the total energy. So P total initial must equal E total before, sorry, P total I mean, P total after collision. Okay, what was the addition before? It was this, the 27,000 plus 1650 V2. And what was the total after? It was exact legit 20,000 if you keep all the decimals or all the fractions. Can someone tell me how should I solve this? Physics is done. Math takes over. Anyone? Raise your hand. Yep. So I have to what? I have to isolate this guy, which means this number joins this number. But what's the price? It has to flip the sign, so it has to be negative. Okay, and now what do? Just what? Just divide that by that. Okay, hold on. There's a problem here. It's not our problem. It's a problem with the question. Can someone see it? Raise your hand. Ammar, who else? It's a problem. There's a contradiction between what we got and the statement in the actual heading of the problem. Ammar, what's the issue here? Again, vectors means what? Plus has a meaning and minus also has a what? Has an opposite meaning. According to us, this is a velocity and it's a minus. We designated which direction to be minus in both instances. No. We have south to be what? Positive, which means what has to be what has to be negative? North, which means if velocity is negative, that means that car, the front black car, was actually moving which way right before it got hit? Forward or backward? He was actually what, or she was actually what? Reversing. But what does the question say? The question said initially it was moving what? Because they said south. Question, it contains wrong information. Which is weird because can you actually tell me, by the way, you have the final answer in the heading of the question. What's the question saying as an answer? 15 kilometers per hour, north. But they said it was moving what? Type on the question. Done. Oh, how do I get, again, how do I get 15? The 3.6 trick, meters per second, kilometers per hour. Remember, meters per second, multiply it by 3.6, because you're going from seconds to hours, you get this guy. By the way, what's the, okay, what was it? I just wondered. Oh, exactly. By the way, question, everyone, listen up. If the question asks for speed, can you ever give that number to me as a negative? No way. Speed is always what? A positive scalar. How about if the question is asking for velocity? Can you keep the minus? Can you ditch the minus and replace it with a direction? 100%. But I need to see what either an interpretation, like a north, or the sign to actually tell me which way it's going. What's the specific situation for this problem? Specific situation, what do we have? 1350 has 3, 1650 has 3, but 24 has, and 72 have 2. So what would this be to 2? Come on. 15. So depending on what the question wants. If the question wants speed, you have got to make a quick therefore statement. Therefore, the speed of the car prior to the collision is what? 15 kilometers per hour. And you can just stop there. But if I ask for velocity, you have to say what? Therefore, the velocity of the car prior to the collision is either that, or you ditch the minus and you say what? North after. Make sense? You have, if I say velocity, I need a direction or a sign indication of the direction. See, that's the beauty of 1D momentum problem. You can do so much work on the diagram and just leave one single quick slide for what? For just the math work. Okay, everyone, let's go to the next slide. All right. By the way, this question is going to be given to you so many times probably in university, but instead of someone what? Releasing an arrow, it's going to be an astronaut trying to change the what? The course of their moving in space. Meaning, after shooting a 28-gram arrow, by the way, 28 grams, heavy or very light? Light, good. With an initial velocity of 92 meters per second. Is that fast or slow? What's so special? Again, small masses have a small what? Remember Newton's first law, something that starts with I. Inertia, which means what? Is it hard to push a 28-gram arrow or is it easy? Exactly. That's why it's easy to what? To speed it up that much. Good. Forward. An archer standing on a frictionless surface travels what? Travels what? Backward. That, by the way, that's an implication of Newton's what? First, second, or third law? Which one? Third, because when the arrow pushes, sorry, you push forward on the arrow pushes what? Backward on you. That's called what? Again, remember the gun story? That's called what in marksmanship or archery? It's called what? Recoil. Recoil. Okay? What was the speed of the person immediately after recoil? Like as the arrow left them, how much did they, like what did they recoil back with? Just how much? Yeah, does that make sense? Yeah, if the mass is small, the speed is what? If the mass is big, the speed is what? Exactly, okay. The question is, calculate the mass of the what? Combined mass, obviously, of the archer plus the what? Plus the bow, because the bow doesn't leave the arrow. Okay, is this more of a collision or technically an explosion? Think about it. Did things come together or split apart? That's a disintegration problem. Okay, everyone, initially, what's my speed? 0. And then something went that way and something went what? Why do you think that's important for astronauts to know? Because if an astronaut is drifting this way and they want to slow down, do they throw something backward or forward? If they throw it backward, it's going to push them what? More forward. They actually want to what? Want to what? Push something forward, which means the recoil will actually what? Push them what? Backward. And in that, speeding them up or slowing them down? Slowing them down. Perfect. Okay. So, what's the speed of everything right before the release? 0, which means what's the total momentum of the system right before the explosion? 0. You got it. Okay, here's a question for you. Hold on. True or false? And by the way, this might actually make it to your a Google form test, next week. Um, if something has a momentum of 0 before, it is possible for both things to shoot together after. Why not? Think of vectors. What is the question is, if a system begins with 0 momentum, it is possible for the exploding parts to go in the same direction immediately after the collision. Raise your hand if you can explain why that is a completely false statement. Josh. By the way, I want a vector-themed answer. Yeah, go ahead. Is a vector? Keep going. Uh-huh. Which, by the way, also means the initial velocity. What's the only way to hold those two identical vectors to cancel each other? Is this correct? Is this slightly more correct? Fully or partially? How about now? If you want to cancel two vectors, how do you orient them? And sorry, two equal vectors. You always orient them what to each other? Which means if one exploding part goes this way, the other exploding part has to go what? Say again? Anti-parallel or opposite, yes. Because any other way, you're not going to get what? A 0 vector addition. See, if they were scalars, that would never work. It had to be what? They had to be a vector. There had to be a vector understanding to it. Perfect. Yes. Nope. Yeah. Okay. Yeah. So these fully add up. These cancel in a way, but add up in a way. Which way do they add up? Sorry. Which way do they add up? Vertically. Which way do they cancel? Horizontally or sideways? They don't have any vertical to begin with, and their horizontal has been completely what canceled out. Exactly. Once you know how one goes, the other one has to what? Has to recoil perfectly 180 degrees from it. Yes, exactly. Okay, so here's the next slide, or sorry, the next shape. Everyone look, eyes on the screen. Now, what's the speed here? By the way, it's exaggerated. It should technically be right after, just after leaving each other. Because usually, when things keep moving, what happens to them? They what? Again, we're saying frictionless and in vacuum, so technically they should go forever in these directions. Okay, what's the mass here of the arrow? 28 grams. What's the speed? It shot at 92. Do we know the mass here? The full thing? No, we want to find that out. But do we know the recoil speed? How much? 0.039 meters or 3.9 centimeters per second. That's all. Yeah, huge mass, huge inertia. They don't recoil as fast. All right. By the way, question. Does it really matter which one gets the positive or minus? Not in this case. Why? Because whenever things start with 0, all directions are equal. Then I go with math. Positive is right, negative is left. You can go the other way. All right. Can I know the full momentum of this guy? Do I have enough information to know the momentum just of the arrow? What do I need? Only two things. What and what? Mass and velocity. Well, guess what? I got both. This one, nah, I know partial momentum because I only know this. I have no idea how heavy the whole thing is. Go ahead. So, P of Archer plus bow, everyone, you can just call it P of mass. if this is way too much to write. Equals mass of archer plus bow. Why do you think this is a minus? Because I designated that direction to be minus, so I just wanted to agree with that. Can I also do the same calculation for the arrow? Absolutely. And here's the good news. I know both numbers for the arrow. There we go. No, go ahead, yeah. Oh, because technically, both the archer and the bow are still together. So whatever mass I calculate, it's not just of the person. It's also added to it the very slight mass of the actual bow itself. Do you see what I mean? Yeah. Because again, the bow was not a part of the released object. Technically, the bow is still stuck to there you go. So technically, I am calculating. Obviously, most of the mass belongs to the person, but technically speaking, it's the combined mass of the of the bow and the archer. That's all. And that's why the question says the same thing. Calculate the combined mass, of the archer and the bow. Yes. Am I now in a place to actually start making things equal together? What do you think? Am I now almost at the same step I was after I finished with the two cars? Yes, I am. I'm just gonna say this whole thing is equal to what? Is equal to what? What do I do with these two? No, just these two. Add them up, because remember, technically, you have to add up everything after and make it equal to everything before. Well, everything before was just what? 0, because nothing was moving. Everything after was this guy with the minus plus this guy. Okay, let's go to the next slide. Yes. Sorry? No. The entire mass is not 0. The momentum of the entire mass is 0. Remember, mass is never 0 in this course, unless you talk about photon. The momentum of the entire mass pre-explosion is what? The momentum, not the mass, because the speed was 0. Make sense? That's why. Yes. Yes, you're right. And when we do the math, it's going to basically, work out to be that. Everyone, next slide. See, by the way, this statement is the same all the time. P total before event is equal to P total after event. Whether you're doing 1D, 2D, 3D, that always happens 100% of the time, regardless of dimension or regardless of the complexity of dimension. Okay, what was the P total before the explosion? 0. What was the P total after the explosion? No. Well, it is 0, but what is it in algebraic way? Exactly. The negative plus the positive. How can we solve that? What do I move to the other side just to make my life simpler? Do I move the number? Oh, no, just the single number? I move the what? The coefficient with its own number. I'd rather move this one here than that. I mean, you could move that, but then you're going to have two negatives on the same side, which in itself is okay. Sorry, on both sides, because the negatives are going to cancel out. But it would look nicer if you do it this way. Josh, that's what you meant, right? Yes. The math will boil down to this statement. The recoil of this should equal to that. What do I do now? Exactly. By the way, do you expect a big number or a small number when you divide 2.576 by 0.039? When you divide a number by a very small decimal, it's like you're what? It's like you're magnifying it. Done. That's it. Does that answer make sense for a mass of a person holding a bow? Yeah, 66 kilograms, about 147, 148 pounds. Yeah, that makes sense. What's the sigma situation from the problem itself? 2, is it? Okay. 92 is 2, 28 is 2, 0.039 is also 2. What would this be to 2 sig figs? 66. Question, everyone. What if this was a plus? What if I forgot to make this a plus? How is that going to completely destroy the logic of my final answer? I would move this one here. I would get a what? Which will not be canceled out because that's a positive. And I would get what kind of a mass? No way. Everything should make sense. Math and physics should be consistent. You should always get what? A meaningful answer for anything in physics. So that should be what? 66. Oops, sorry. 66 kilograms. Again, that's what? Combined. How much of it is the archer? How much of it is the bow? Who cares? 1% archer, 99%, sorry, 99% person, 1% device. Doesn't matter. Ladies and gentlemen, that's basically what? That's basically the 1D example. Okay, what's up? Sure. Okay, one more problem. Come on. 10 minutes before we usually stop. Consider a collision in one dimension that involves two objects, mass 4.5 and mass 6.2. Okay, the larger mass is initially at what? By the way, this get used to these kind of questions. An object in motion hits an object at rest. How many possible scenarios are there afterwards? A bunch, right? What could happen? By the way, could it ever be that one object that is not connected to a wall stays put and the other one just perfectly bounces? No way. If this one is almost, okay, the only way that an object never moves is if it has how much mass? Think. How huge? Exactly. Only an infinitely heavy mass would what? Would never move, right? But obviously, every object is not infinitely heavy, which means what? It will slightly what? It was, come on. It will slightly what? Move. But still, the other object will what? Will bounce off. Oh, are you talking about infinitely heavy or not? Oh, whatever energy was stolen here, sorry, whatever energy was imparted to the forward moving now is going to be stolen from what? From whatever it needs to what? To bounce back with. Because conservation of energy. Right? Again, whatever you lose is gone. You only can bounce with as much kinetic energy as you what still have after giving some to that. Okay? By the way, technically at the end of this unit, I have to show you problems where you both do conservation of energy and also what? Momentum in the same problem. By the way, they never go split. They always happen together. Okay, come on. So one object is moving. One object is what? Standing. After the final, the final velocity of the larger one is what? Come on. 10 meters which way? Of course. Could this ever like start moving backward? No way. You hit, one of two things happen. Either this one moves forward and also this one moves what? Like they both move forward, but this one speeds up and this one slows down. Or what? This one moves this way and this one moves what? That way. Apparently, the final velocity of the larger object is 10 meters per second east. Calculate the final velocity, which means momentum, sorry, magnitude and direction of the smaller one. Okay? Let's sketch a diagram. Everyone, I hope I gave you enough space here. Again, just sketch two small circles for each object. Okay. Initially, which way was the direction of the moving object? Which way is east? Usually. Right or left? Come on. Which way? Right. So I'm going to sketch the moving one here and the standing one right here. Okay, go ahead. So go ahead with, just sketch one circle bigger than the other because one of them is what? One of them is what? Heavier. No, heavier. Remember, it's the size is just to represent the mass. That's all. So the lighter object was moving. I'm gonna call it 1, and it hits the bigger one. Sorry, I mean heavier. What was the speed of this one? Pre-collision. Zero. So I'm just gonna put the vibration lines I always do for stationary object like this. Okay, what was the speed here? Come on, what was the speed here? No, this one. 16. So I'm just going to put 16. Oh, which direction do you think should be positive throughout the whole problem? Right or left? East, which is right. Good, thank you. So everyone, this is plus and this is minus. What's the mass of this one? 4.5 kilograms. What's the mass of this one? 6.2 kilograms. Okay. How am I going to change the diagram to reflect what happened after collision? Okay. Now this one moved which way? Do I know right now if this one kept moving forward or backward? Does the question tell me? No, it doesn't. So you know what? This is what I'm going to sketch. I'm going to sketch this one moving this way. Go ahead. This is number 2. What's the speed now? Oh, this is the 6.2 kilograms. What's the speed now? How much? 10. I have no idea which way this is moving. I don't know. Did it move forward? Did it come to a stop very quickly and bounce back? We'll let the math answer that question for us. However, do I change the positive minus designation? No, you never do. Otherwise, you're flipping the problem after, which will confuse the hell out of you. So, same thing. This is still 4.5. Okay. Now let's go to the last slide and start with the what? With the calculation, because we don't have any more space under this. I'm just gonna give you 30 seconds to finish copying this. By the way, question, everyone, listen up, because that's gonna lead into tomorrow. What if the two objects were not colliding? Look, everyone, such that their centers of mass are lined up. What if this one was elevated just a little bit? Can you think what's going to happen? Again, they're not colliding, center lined up with center. One of them is offset, up or down, doesn't matter. It changed. Ammar, what do you think is going to happen? Like, let's say I raise this one a few millimeters up. Exact. Playing pool, right? This one could now bounce upward, while this one has to what? Exactly. That's tomorrow's what? 2D collision. Okay, everyone, let's go to the next slide. Okay, come on. Can someone tell me what's the momentum of this one right here? What's the momentum of this ball right now? Come on, everyone, focus with me for 5 minutes, no more. 0. How about this one? Does it have negative or positive momentum? Why positive? Because with which way is it moving here? With whatever we designate to be positive. So everyone, let's start. You know what? I'm gonna start with the statement itself. P total initial equals what? P total final. So let's start. P, that's in your next slide. P total initial must equal P total final. Okay. What's the mass of this one? 4.5. What's the velocity? Minus 16 or positive 16? Good. So I want you to write it even with the 0 in the next one. So go ahead. 4.5 times positive 16 plus 6.2 times just what? What's the speed of ball number 2 right before the collision? 0. Thank you. I know this whole thing will be 0 this part, but I still want you to write it down. 0 equals. I want someone now to do this in the same spirit. Raise your hand. Ammar, go for it. 4.5 V1 final. Do you know if it's positive or negative? No, we don't. The math will what? Will lead us through the way. So 4.5 V, you said what? 1, ball 1, final. Thank you. Plus what? 1 second. Plus 10. Sorry, I like to start with the mass first. times negative 10 or positive 10? Positive 10. This way is positive. Good. Physics is done. Let's solve this. So what happens here? Well, the good news is this one zeroes out. So what's 4.5 times 16? That's 9 times 8, which is 72. So this whole thing is 72. Equals, I don't know what this is. I just know it's 4.5 V1F, as Ammar said, times, sorry, plus, that's just a what? 62. All right. Keep going. Sorry. Oh, good. Sorry, I thought I... Yes, we're still good. Hold on. How do I solve this? Come on. Move this guy here to 72 minus. Which means V1F equals 10 divided by... Oh, go ahead. Good. How much is that? 2 point something. 2 point what? 2.2 infinite. Positive or negative? What did we get? What does that tell you about the direction? What does that tell you? Sorry, my bad. How do you reconcile this with that? What does that tell you? Ahmed? This one is going to bounce backward or still move forward? Forward, but with what speed? Same speed as before? Faster or slower? Of course, slower. It went from 16 down to what? It went from 60 meters per second here to 2.22. Here's my question. Okay, Josh, is the speed conserved? I don't know. Let's see. What was the speed here? What was the speed here? So if you add the speeds or velocities, what's 16 plus 0? 16. What's the speed here now? What's the speed here? No, here. 10. What's 2.22 plus 10? Is velocity conserved? See, velocity is never conserved. The effect of velocity is the conserved one, which is both kinetic energy and what? And momentum. Is it making sense now? Everyone, never think that, oh, whatever velocity was lost here should transfer here. No. Whatever energy and momentum lost here is what was transferred to the other object. Done.